Welcome back.
Okay, it's starting to get weird, but I'll roll with it. Now that we've talked about Maxwell's equations, and we've talked about wave solutions to Maxwell's equations, we've discovered something that's sort of, I don't know, deeply unnerving. That Maxwell's equations give us wave solutions, and those wave solutions predict a wave speed, which happens to be equal to 1 over the square root of mu naught epsilon naught. Of course, on the surface, that's not deeply disturbing, except when we couple this to the fact that we know that Maxwell's equations are true everywhere. They're true on the Earth, they're true in the galaxy, they're true in the intergalactic medium. And all of these different reference frames are moving with different velocities with respect to each other. And so we would expect all of those reference frames to obey Galilean relativity, where I have normal addition of velocities. It's that old problem of throwing a ball on a train and noticing that the person on the train sees the ball travel at a different speed than the person who's walking next to the train. But what Maxwell's equations tell us is something that's contradictory to that. That the speed of light, the speed of electromagnetic waves, does not depend on which reference frame you're in. So if we're watching a light pulse, either from the side of the train tracks or on the train, both of us see that light pulse, both of us see that electromagnetic wave traveling at exactly the same velocity, which is given by these natural constants that we really tried pretty hard to actually measure in the lab. So if I apply a Galilean transformation, where I take z and let it go to z plus vt, so that is that's the transformation where I go from looking at, say, the train and the person standing next to the train, and I rewrite the electric field is equal to cosine z minus ct, as the electric field is cosine z prime minus c minus v times t. Well, it's right here. If I do this transformation on the solution to Maxwell's equation on the side of the road, and I try to calculate what does the electric field look like on the train that's going on at some velocity v, I get the wrong answer. This idea that Galilean transformations can help us to understand wave speeds from Maxwell's equations is not good enough. We do not have consistent solutions to Maxwell's equation given transformations where I only allow space to transform. If I think about that for a second, that means if I'm going to preserve the speed of an electromagnetic wave, and if I go from one reference frame to another where we're going to disagree about where z equals 0 is, we're going to disagree about who's at rest in the z direction, we're going to disagree about the z coordinate. In order to have speeds in z remain invariant, I'm going to have to transform z, but I'm also going to have to transform time. And that's the only way around it. Because I have to be able to go from one inertial reference frame to another, because after all, we've seen that Maxwell's equations work in every reference frame. And if I transform from one reference frame to another, and therefore I'm changing my spatial coordinates from one reference frame to another, then I have to allow the time coordinate to change as well in order for the speed of light to be the same. If you're like me, a little graphical interface sort of helps at this point. So this is your traditional two-dimensional axis, and you are used to seeing time on one axis and, say, position on the other axis, and then we draw curves that tell us how things change in position with respect to time. Well, in relativity, we're going to have to upend all that, so let's get rid of everything that I wrote. Because, one, we want to break our intuition about what it means to see space and time on a diagram. But we also want to break ourselves of the idea that time is now a dependent coordinate. Because time is going to be the same as space. And so we have to treat them with the same amount of, respect and individuality. And so on this coordinate system, I'm going to let space go left and right, and I'm going to let time go up and down. Okay, so if I'm going forward in time, I'm going up this graph. If I'm going left or right, I'm going left or right in this graph. Okay, this is a one-dimensional universe, but that one dimension is going to represent everything else that's going on in our universe. To make our units better, after all, space is usually measured in space is usually measured in meters and time is usually measured in seconds, I'm actually going to do a quick coordinate transformation to, oh, look at that, to change my time coordinate from just t to c times t. And when I go from just c to c times t, then I'm basically saying I'm going to be measuring my time in units of meters, because I'm taking everything in seconds and I'm multiplying it by meters. At first, you might be a little bit uncomfortable with this because the speed of light in meters per second is kind of a big number, but really it's just a choice of units. And when I go to problems where I really have to worry about the velocities involved in moving from one reference frame to another in special relativity, it turns out that measuring time in these units is actually a pretty good idea. And so when something travels along this diagram, it's going to be traveling through time upwards, right? So things always get older. Trust me on that one. And so a path on this diagram that represents somebody traveling through space would look something like this blue line, which is what we call a world line, which shows the path of an object as it's going through time. And this thing is sort of going a little bit to the right and then turning back and coming a little bit to the left. So now that I have that construct of space and time, as a diagram, I want to take a moment and I want to talk about a difference between things that we measure for convenience, so maybe we can do calculations, and things that are actually physically real. Okay, an example of this is if I have 2 points in space and I want to measure how far it is from one point to the other, that distance is something that's real. Right? The distance between the distance between me and my coffee cup in the morning is a real distance that's very, very meaningful. What's, for lack of a better word, fake is the coordinates that I use, or even the units that I use to represent that distance. Right? So if I were to put if I put me at the origin and I measure the radial distance using polar coordinates to my coffee cup, that's as good a description as if I were to use Cartesian coordinates, or if I were to set the origin somewhere else. None of these things really matter when I'm talking about the physical reality of distance, but they are a choice that I have to make in order to do calculations. I might not be able to say measure the distance until I've defined a set of coordinates. The same is true for space and time. Where I am in space and time is a coordinate-dependent statement. I have to choose my inertial reference frame, which is a choice of how I'm going to measure space and time. But that in and of itself isn't real. The only real thing that I can do is try to construct some idea of distance in space-time, and the idea of constructing something that looks like distance in space-time is called the interval. Interval is a great word because intervals we use to both mean distances. I used to be on the track team. Maybe some of you were too. When you did intervals, right? That was a measure of distance. But interval can also be a measure of time. And in fact, the interval, as we're going to define it, is something that captures information both about separations in space and separations in time. So the interval itself is this quantity delta S. So the interval is going to be this change in S, or delta S, which represents some space-time interval. I'm going to calculate that interval by taking the separation in CT, right? So this is a coordinate idea. I'm going to take how far apart are two events. I should mention that word. So a point here on my space-time diagram is called an event. After all, it refers to not just a location, but also a location and a time, so we call that an event. If I have two events, say here, I can start to talk about delta CT, how far separated are they in CT, and I can talk about how far separated are they in space by drawing a right triangle on this diagram. Now, your intuition always has been, in Euclidean geometry, to calculate the distance between 2 points on a plane by adding the sum of the squares of the two legs of the hypotenuse. But here, because space and time affect things differently, I actually compare the difference in time with the difference in space by subtracting them. So delta CT is the separation in the CT direction. Delta X, delta Y, delta Z are separations in the spatial directions. And therefore the interval is the difference between the separation in time and the separation in space. Okay, let's do an example. So I have three events. A is located at the origin. B is located 3 meters later, right? Its CT is equal to 3 meters. And C is located at x equals 4 meters. So I can start to calculate intervals. Let me start with delta SAB squared. So this is the interval from A to B. Well, the A to B are separated only by CT. And so delta CT is equal to 3 meters squared. And then, of course, minus 0 because delta x squared is 0. Well, this number is 3 meters squared, which is greater than 0. Which means that A and B are separated more in time than they are in space. And so this is something that we're going to call time-like. On the other hand, if I calculate the interval from A to C, I get 0 because A and C are located at the same value of CT, minus 4 meters squared. Well, this thing is less than 0. So the interval squared between A and C is minus 4 meters squared, but that's less than 0, so we call it space-like, because the events A and C are separated more in space than they are in time. Now, I can do a slightly more interesting example if I try to measure the interval between B and C, right? So delta S squared BC, well, the time separation, the delta CT is going to be 3 meters squared minus 4 meters squared. Well, I can already tell that this thing is going to be less than 0, and so these are also space-like separated. In the case that you happen to get a delta S squared that's equal to 0, this is something that's called light-like. And in our next lecture, you'll see exactly why we call it light-like. But there are basically only three types of answers you can get out of an interval. Either the interval squared is positive and it's time-like, the interval squared is negative and it's space-like, and the interval squared is 0 and that makes it light-like. Okay? So calculating intervals is a way of determining what the relationships between events are. And although we won't talk about it until next time, once you've determined that two events have some relationship, say they're space-like, say they're time-like, say they're null, say they're light-like, you end up with always having to preserve that relationship. Two things separated by a time-like interval will always be separated by a time-like interval. Two things separated by a light-like interval will always be separated by a light-like interval. The interval is the thing that's real. It's the equivalent in Euclidean geometry to the distance. Doesn't matter what coordinates you use, it always has to be the same. So your take-home messages are these. First, space and time are the same. Space and time are actually the same. If they weren't, if space and time were special, or time was special, or space was special, then Galilean transformations would be true in all areas of physics. But special relativity, as a consequence of Maxwell's equations, tell us that space and time are the same. And from that, we find that the interval is the important invariant physical quantity that we can calculate when we start talking about the fact that space and time have to be considered on the same plane.